Hello students, this is Professor An King, and this is a continuation from last Thursday on the Chapter 13 lecture. So let's go ahead and get started. So where we left off last week, we were talking about linear inertia force and with respect to dynamic equilibrium. So you remember the block that we had on the ground. We have an applied force going to the right and a force of friction going to the left, and the normal force, which is based off of the weight force. And in this particular case, the normal force is going to equal to the weight force. And we also remember how we applied those particular forces, the applied forces, at an angle, and we had to resolve them into their components so that we could figure out what that normal force is, so then we could calculate the force of friction. And so again, your force of friction was the mu sub k times the normal force, and mu sub k represented the coefficient of friction. The other type of example that we did was one on an inclined plane, and the weight of the box is broken down into two components, your mg cosine of theta and your mg sine of theta. And in this particular example, the box, we would actually have to figure out what the friction force is if the box was just free to slide down the inclined plane. But of course, then we'd also need to know what the coefficient of friction was of the box itself. So knowing that equation, we would say the force of friction would be the coefficient of friction times the normal force, or the coefficient of friction times the weight, or mg, times the cosine of theta. Now, where are we going? Well, where we are going. And I mentioned last week we could talk about a block over a pulley pulling another block. So what if, in this instance, we had the weight of the block and we wanted to find out, based on the normal force, in this particular case for the block on the left, the normal force is purely the weight, okay, because we don't have any angled force. And keep in mind that the torque or not the torque, but the tension in the cable is constant throughout the cable. So whether the tension over here on the right side versus the tension over here on the left side, they're both the same tension. And so if we are saying that this weight is pulling down on the box, what is the force of friction that is necessary to keep this little box from moving? So let's look at an example. The question I have is, if the big M, the mass, is 1,000 kilograms, then what does the mass, the little m, have to be to keep the system in equilibrium, assuming that we have a coefficient of friction of 0.3. So let's examine the right side first. Right side we have, again, we have the tension in the cable, we have the big mass of 1,000 kilograms, and so we calculate the weight of that to be 9,810 newtons. Now looking at the sum of the forces in the y, if we're in equilibrium, that means there's zero. So the torque has to equal the weight in this, not the torque, the tension. So we look at the forces in the y equals 0. The tension in the cable must equal the weight, which equals 9,810 newtons. And remember, the tension is going up, the weight is going down. So now we can examine the left side of the example. And again, we have the tension in the cable to be 9,810 newtons. And so what we're trying to find out is that what mass is necessary to keep this thing from moving. So if we look at the force of friction, again, we're going to set that equal to the coefficient of friction times the normal force. Or in this case, since it's flat, we have the coefficient of friction times the mass, the little mass, times the acceleration due to gravity. So if we plug in some of the numbers, we get 0.3 times the small mass times 9.81 equals 9,810 newtons. Solving for m, we get an m value of 3,333 0.33 kilograms. Now let's move on to the next topic of discussion, which would be angular inertia. Now from your text, you'll notice that we're going to be talking about, in this case, we are talking about torque, which is the moment of inertia, mass moment of inertia, about the center of mass, times the angular acceleration in radians per second squared. So we can get a torque value of Newton meters. The mass moment of inertia is usually represented by kilogram meters squared, and like I mentioned, the angular acceleration is in radians per second squared. Now in the English system, torque is represented by pound-foot or foot-pounds. The mass moment of inertia about the center of mass is in slug-feet squared or foot-pound second squared. Not per second, foot-pound second squared. And angular acceleration is radians per second squared. And if you recall from your statics, you can usually get the mass moment of inertia from table 9-2 or by calculating from the radius of gyration equation, which was out of section 9-7, where you had your radius of gyration k equals the square root of the mass moment of inertia I over the mass, or the mass moment of inertia I equals the radius of gyration k squared times the mass. So let's look at an angular inertia example. So if we had the spin cycle of a typical washer drum, thing that you wash clothes with, to be 635 revolutions per minute, and it takes a washer drum 5 seconds to get to this speed, what is the torque created by the drum if the mass moment of inertia is 15 kilogram meters squared? So first what we calculate is the final angular velocity, which is 635 revolutions per minute, and we need to convert that into radians per second. So as you can see, all we do is multiply it by the 2 pi radians over 60 seconds to give us 66.497 radians per second. Now we already know, since we're talking about starting from rest up to this speed, the initial angular velocity is 0 radians per second. And if you recall your equations, we can use omega final equals omega initial plus alpha t. And if we could solve for the angular acceleration and then substitute, you could see that we get 13.3 radians per second squared for the angular acceleration. And so going back to our original equation of torque, which is the moment of inertia times the angular acceleration, now that we know what the mass moment of inertia is, because it was given in the problem to be 15, multiplying by this calculated value of angular acceleration of 13.3 radians per second squared, we get 199.49 Newton meters. So what does all this mean? Well, we can calculate, just like we did before with the pulley, we can actually throw in some type of machine into the system that has a rotation, like a winch or a motor. So then we can determine angular dynamic equilibrium. Now, I want to bring to your attention the textbook in and of itself made one slight error on the example 13-8. Now let's go ahead and read this problem. It says a power-driven winch is used to raise a mass of 300 kilograms with an acceleration of 2 meters per second squared. The winch drum is 0.5 meters in diameter, and that's located on the left where you see the word torque, and has a mass moment of inertia about its center, I sub c, equal to 8 kilogram meters squared. So what torque must be applied to the winch drum, which is figure 13-15? Now, so what we need to find first is the rope tension T. And using a free body diagram of the 300 kilogram mass, or figure 13-16, okay, what we're going to do is sum of the forces in the y equals 0. So we have the tension in the cable, and then we have the weight component, which goes at 300 times 9.81 equals 2943 newtons. Now, where the error is that it says that a power-driven winch is used to raise the mass. So the net change in direction of that 300 kilogram mass is to go up. But the textbook actually talks about when it calculates the forces in the y, it actually shows that the mass times acceleration is going down. So we have to actually fix that. So what we're going to do is look at the mass times acceleration going up, which will change some of the values. The format and the process of the solving for the equations is still the same. So our equation will be tension of the cable plus the mass times acceleration minus the weight equals 0. Whereas the book says the tension in the cable is tension would be minus the weight minus the mass times acceleration, because they had that mass acceleration going down instead of going up. And this object's going to be accelerating upward. So if we substitute our values, we have the mass of 300 kilograms going at an acceleration rate of 2 meters per second squared, minus the 2943 in the weight, we get a tension in the cable of 2,343 newtons. Somewhat different from what the textbook has. So we're going to use that value from here on out throughout the solving this problem. And the drum still has a tangential acceleration equal to 2 meters per second squared acceleration of 300 kilogram mass. So it's still accelerating tangentially, okay? Even though this is the tension in the cable, which is just pulling this way, it's accelerating basically to the left here, okay? Because remember, we're pulling it up. All right, so what we would do is go ahead and solve for that, knowing our linear to angular relationship that we have, which is the tangential acceleration equals the radius times the angular acceleration. What we need to find out here is what the angular acceleration is. So we go ahead and rearrange the equation so we have the tangential acceleration divided by the radius, which is 2 divided by 0.25, or it gives us an angular acceleration of 8 radians per second squared. Now, so if we take the moments about the center of the drum, we get the following. The sum of the moments about the center has to be equal to 0. Now, if we look at the drum, you have a torque going counterclockwise. You have this IC alpha going clockwise because it always goes in the opposite direction of the angular acceleration. Okay, so this IC alpha will always do that, go in the opposite direction of the angular acceleration. And then we also have to deal with this 2343 Newton force, which is going to create a torque in and of itself. So we would say that the torque minus 2343 times 0.25, because we're going to say that the direction or the positive value of the moments about the center of the winch or the center of the drum is going to be counterclockwise. So everything counterclockwise is considered positive. Okay, so we got minus 2343 times 0.25 minus this IC alpha, because remember the IC alpha is going clockwise and so is the 2343 going clockwise. So those have to be negative. So if we plug in some more values, solve, we get this. And then finally solving for torque, we get that to be 649.75 Newton meters. And of course that'll be counterclockwise. So this is the basic setup for these types of equations when you're dealing with dynamic equilibrium and dealing with torque. On Thursday, we hope if you have any questions, go ahead and try to work on some of the problems that we have assigned in these sections, and we'll go into a little bit more detail of some of the next part of this section. Take care and have a nice evening.